Schrödinger equations, please.
Okay, so first of all, thank you very much for the invitation. This thank is to the organizers. It's a pleasure to be here. So I decided to do the first part on the blackboard because I think those kind of meetings are very suited for blackboard talks, and I kind of want to foster a little bit this tradition. So I will speak about post-processing procedures of given plane wave approximations to nonlinear Schrödinger equations. So we have seen yesterday a little bit DFT, density functional theory. So this is kind of the end goal, and I will show numerics at the end on the laptop, not on the blackboard. Some results, numerical results of this procedure. But for now, we focus on what is somehow for us a toy problem for DFT is the Gross-Pitaevskii equation. It is used to model Bose-Einstein condensates, which is somehow the mean field, or the Gross-Pitaevskii equation describes the mean field limit of interacting bosonic particles. But in contrast to fermionic systems like electrons, you have the nice property to have symmetry in your wave function, and in fermionic problems you have antisymmetry, and you might think that is somehow you have similar properties, but antisymmetry is much more difficult to deal with than symmetry, because here everything collapses to a three-dimensional problem, and in fermionic systems you still have this big beast of 3n-dimensional PD, the Schrödinger equation. Okay, good. So the continuous setting is the following. It's a constraint minimization problem. So you describe a Gross-Pitaevskii energy functional, which is the integral on some domain. For me, the domain, let's say, is like a square or a cube in 3D, and we're looking at the periodic problem. So this is, in all the talk, you do have periodicity, and this is coming from material science, where you have crystalline structures, so doing an approximation that you have just a unit cell is a very reasonable thing. Okay, so you have some kinetic term. You do have presence of an external potential V. So V is a real valued Hs and periodic function over omega, and it's a multiplicative potential, so it's just a multiplication. And so S is supposed to be larger than D over 2, where D is the dimension. Okay. Plus you have here, we model the nonlinearity by a term which is, let's say, 1/2 u to the power 4. This is your energy functional. And then what you define to be the, let's say, the terminology from electronic structure computation is you would define the ground state energy E0 to be the infimum over all V that are periodic H1, such that the norm, the L2 norm, is equal to 1, and this is coming from the fact that you're looking for a probability density function which should have norm 1, and you do this. Okay? So you can derive the Euler-Lagrange equations, which are given in strong form like minus Laplace u plus vu plus u cubed equals to lambda u. U should also be of norm 1. And somehow the lambda has two meanings. Lambda on one hand is the Lagrange multiplier associated to the constraint that in here we should be of norm 1, but it has also the meaning to be the, and we're looking here for the lowest eigenvalue, since we want to minimize the energy functional. So it is also the lowest eigenvalue of the mean field operator or Hamiltonian HU, where HU is given by minus Laplace plus V plus U cube, U square. Since you have that HU applied to U must be lambda U, okay? So we know there is uniqueness, so there exists a unique minimizer U up to a global phase. So if you're looking only for real valued solutions, then you have two, you have U and minus U, and so there exists a U that is non-negative, okay? Good, and that's somehow the exact or the continuous setting. And then you want to go to the discretization. And first of all, you introduce basis functions which are plane waves. So you have to scale them in order that is orthonormal basis functions. EIKX, this is the basis function EKX. Now, all the k's, the wave vectors, are in the so-called reciprocal lattice, denoted by R star, and these are all the vectors such that EK is indeed periodic on mu, on omega. Okay, so this is the basis functions. So you can define the approximation space to be the sum over all suitable vectors, wave vectors, but that their modulus is bounded by a certain n of some coefficients Vk times Ek, and then you also assume that this relation holds, where this is the complex conjugate, in order that this function is real. Okay, this is your approximation space. So if you look in reciprocal space, what you do is you have here some regular lattice here, and you take all the wave functions that belong in this ball of radius n. Okay. A very important notion is the orthogonal projector for any HS onto the approximation space, and this is just if you have an infinite series of a Fourier series, then if you apply here the Pn, you just take those sums that indeed belong to this ball. Okay. So you can also define its orthogonal, the orthogonal projector on the orthogonal complement. So from H periodic S onto Xn periodic by saying that this is identity minus Pn. Okay, there's nothing really new here. But then you do the same procedure and you define your discrete energy to be the minimum over Vn in Xn such that the norm is equal to 1 of the energy function in Vn. And you can derive as well the Euler-Lagrange equations. So the first order optimality condition under the constraint that the norm is equal to 1, and then you get to something like a weak form that reads like un plus vun plus un cube against Vn must be lambda n un Vn for all Vn in the approximation space. So this is a variational approximation. It's a Galerkin discretization. Everything is standard. So instead of writing it like this, I can say that testing with Vn is like applying a projector, the projector Pn to the left. Now you have that the Laplace operator and the orthogonal projector do commute. If you discretize the Laplace in Fourier series, you get a diagonal matrix. So they do commute, which means I can this equivalently write as minus Laplace plus Pn of V plus Un square times, I can insert here project as well, if I want, applied to Un is equal to lambda n Un Vn. Okay, so now for the remaining I call this W, and this is the operator Hn hat. Okay, and Hn hat is somehow the Hamiltonian here, which is an operator from Xn to Xn, and we have that Hn hat times Un is lambda n Un, but note that Hn hat itself depends through the nonlinearity from the solution Un. Okay? So good so far. We would like to compare this operator to the exact mean field operator, but they are not acting on the same spaces, so we extend this to be operator on the full space. So let's say we define the operator Hn as going from H1 to H minus 1, exactly in the same way. So Hn is minus Laplace plus Pn Wpn, okay? And if you look at the discretization in a schematic view, where we here represent the operator in terms of its component in Xn and in Xn orthogonal and Xn orthogonal. So in here you have this portion that I called Hn hat, but you see, because this is a diagonal matrix, this you have a projector on the left and the right, you have an off diagonal that is 0. And in here, the only thing that is seen is the Laplace operator. Okay? So the whole kinetic energy here is in here, but the L2 terms, they are filtered out, which shall be essential in the following. So now, since we have now this extended to a larger, in a larger sense, we can ask the question, how do they relate? And what I'd like to, or the key idea is to say that the exact mean field Hamiltonian is Hn plus a correction which I call Wperp. Okay? So now you can do the math and quantify, of course, what Wperp is. Wperp, it's a bit lengthy, but first you have to remove these two orthogonal projectors. So it's Pn W Pn perp plus Pn perp W Pn plus P and perp Pn perp plus, then you remove them, but you're still stuck with the Un square, but the exact one has the U square. So you add U square and you extract Un square. Okay? That's the definition. And now what you do is you introduce a perturbation parameter. And a perturbed Hamiltonian which depends on beta, which is the discrete one, plus beta times this Wperp. And we see in consequence that h of 0 is the original discrete Hamiltonian. This problem we can solve. And h of 1 is the exact Hamiltonian, which is somehow what we want to approximate. Okay, now the point is that Wperp is a compact perturbation of the discrete one. So this is small compared to that, and this is manifested in the way that if you have Wperp times the resolvent in operator norm tends to 0 as n goes to infinity. And in consequence, you can apply perturbation theory, and you're guaranteed that the following series are converging, namely if you have here the perturbed Hamiltonian, plus then you write your solution as a sum of powers of beta times corrections, and the same for the eigenvalue. There we have uj, that this series converge for n sufficiently small. Sorry, sufficiently large, of course. Okay, so whenever n is sufficiently large, we know it's converging even for beta equals to 1, and we can compute these corrections, first order corrections and so on, in order to improve the quality of the approximation. Okay, so you can look at the zeroth order term. The zeroth order is hn u0 equals gamma 0 u0, and you recognize immediately that is the plane wave approximation you have. Okay, so lambda 0 equals lambda n, and u0 equals un. Okay, there is nothing, that's not it, not rocket science. The first order correction, then you have here a hn, but then the u1 here, because you have 1 power in beta. And then you have the beta here, so you have the 0th power here. So you have Wperp times u0 equals lambda 0 u1 plus lambda 1 u0. So let's focus first on lambda 1. And what I'm hiding here is a bit the strategy of the intermediate normalization, which requires that ui and uj are delta ij. Okay, so they're orthogonal. So you can test here with u0, un. Okay, this means that all the terms with u1 will vanish. So you can directly deduce that gamma 1, this is of norm 1. So gamma 1 is equal to this term here. You multiply by gamma 0, so you have un Wperp un. Now what is Wperp, right? So if we have from the right and the left a discrete function, here this one is 0, here this one is 0, this one is 0, this term is not seen, it's only this one, this term is seen, because you have the orthogonal projector either on the right or the left. Okay, so this means that here this is given by u square minus un square un square. Okay, so if you know from a priori estimates that this is a small term because it's a L2 norm, and you have the difference of the square, which also involves the difference. So a priori we know that this is a small term. Okay, then you can go to the u1 and look what is the equation for u1, and you put this term on the other side. u1 is equal to minus Wperp u0, so this is un plus this lambda 1 that we know here, un. And this gives us an equation we want to compute. Okay, the holy grail here is to compute this u1 and then add it to un and hope for a better quality, better solution. Okay. Wow. Well, this will be okay. Thank you. Yeah. Okay. So what is minus Wperp un? Okay. Again, relying on the definition of Wperp, we only see that there are two terms surviving. This is minus Pn perp W un. There was a Pn here in between, but since un is in the space, we can neglect it. Minus u square minus un square times un. Okay? So in this, we therefore have un minus lambda n u1 is equal to this part, Pn perp W un minus u square un square un plus lambda 1 un. Now, this is all small by a priori results. It's not that I'm neglecting it, but I'm estimating it. Okay? This means when we look for a perturbation or a first order correction, I do solve Hn minus lambda n u hat 1 or u tilde, and I'm only considering this this part, and I'm neglecting this one. But afterwards, when I state the theorem, I have to account for this one that we neglected this one. Okay. So what is this term? So look at the residual. The residual is minus Laplace plus v w minus lambda n applied to un. That's by definition the residual, because this w is v plus un square. Okay? Now, what you can do is to insert and subtract the following quantity. So you write this as minus Laplace plus Pn W Wpn minus lambda n un, and then you added this, but you don't have this, so you have to add here this correction, which is W minus Pn W Pn of un Now this guy is equal to 0 because lambda and un are exactly the solution of this problem. And you remained with the discretization error and the nonlinearity error, which is combined in here. And this is nothing else than identity minus Pn W un. Okay? So this is, in other words, Pn perp of Wn, the quantity you want to have in here. Okay? So now the final remark or idea is to acknowledge, since you have a Pn perp here, that this is in the orthogonal space. So this is crucial if you look at this operator here that you have to invert, since, as we have seen before, we have here Hn hat 0, 0 minus Laplace. And if the operator is only restricted to the orthogonal, then you only have here this diagonal operator, and by magic this becomes a linear matrix to be inverted. So this is very feasible, and you can then write, and you're able to compute as minus Laplace minus lambda n minus 1 of the residual. Okay? And suddenly everything simplifies. You have to compute the residual, which by definition somehow lives in the Fourier space on the outside of the approximation space, so only on the outside. So you have to introduce from a practical level a larger and residual where you actually compute the residual. And once you have computed that, you just have each entry in the Fourier vector to divide by this scalar quantity. And so you need two FFTs per eigenvector. Since this straightforwardly generalizes to any eigenvector if you're looking for more. And what you can prove then is the following. And so that's a good occasion to recall my co-authors. So this is in collaboration with Eric Kanches, with Geneviève Dusson, Martin Voralik, and Yvon Madet. Then you can prove that U, the exact solution, minus Un minus Un or U tilde 1, this computed correction here, UN1, is bounded by constant times n to the power of minus 2 times the error in the H1 norm of U minus UN in the H1 norm. What does it mean? You gain 2 orders in n with respect to the unperturbed approximation, and this is irrespective on the regularity of U. And on the same for the energy, you have the energy of UN, let me call it here just the perturbed one. You have the same that you gain 2 orders with respect to the non-perturbed. Okay? Now I'm switching to the computer, where I will first show you a simple numerical illustration on the one-dimensional Gross-Pitaevskii equation. Yes? Yes, of course. This is by we assume that it is infinite, okay? And we see in the practical result, coming back to this, that at certain point, if you go further away, doesn't change anything. I mean, somehow the interesting information is around here, because those coefficients in the residual, they decay. No, the theory doesn't account for that. Maybe you could do a numerical analysis on that, how to quantify this, at least in the asymptotic regime. Yes. Yes. Yeah. So this is asymptotic in n. So if this is increasing, but this is supposed to be infinite. For practical purpose, we do have to truncate because the residual is a infinite dimensional object. Okay. So what do we see here is the 1D Gross-Pitaevskii equation. So first in red here is the convergence of just the brute plane wave approximation. In black is if you do add this first order perturbation to it, and you get 2 orders of convergence rate extra compared to this one, and here this is the 2 orders because this is the quotient between the two. Okay, then let me finish on what was also in the title, Kohn-Sham DFT. I have to be very brief what it is, but at the end I give you numerical results showing that we can also extend the theory to it. Okay, so the Kohn-Sham model is to describe the electronic state of a molecule. So you're looking for the so-called Kohn-Sham orbitals. These are n orbitals and functions in H1. They need to be mutually orthonormal. And you look therefore at this Stiefel manifold of possible candidates. And in the full or in the n-body Schrödinger equation, you have the wave function, but thanks to the Kohn-Hohenberg theorem, you can reduce everything to the electronic density. And the electronic density is defined through these orbitals in the following way, that you sum up the squares of these orbitals. I mean, there could be now a 2 hours lecture on DFT, that's not the purpose here. But as before, it is a constrained energy minimization. We do want the orbitals to be in this manifold, and we minimize some Kohn-Sham energy functional, where now we have several eigenvalues, and they are summed up here. Plus, we have a local potential, some non-local contributions, some Coulomb interaction, and some exchange term. So first, this is the most of the part is the attraction of the electrons to the nuclei. It's just a plain Coulomb interaction type of the nuclei. And this is a non-local operator due to the presence of what's called pseudopotentials. But the basic idea is that the core electrons, they are not reactive and no chemistry is happening there. So you remove them from the system, and you add around each nuclei some pseudopotentials. So this has 2 effects. First, you reduce the number of orbitals you have to solve for. And secondly, this has a smoothing effect on the Coulomb kernel, or on the Coulomb potential, which smooths out this negative density of the core electrons with the positive point charge of the nuclei, gives you more regular solutions, and you need less plane waves to approximate your solution. Then this is just the Coulomb energy. So if you have some density, you build the Coulomb potential through the Green's function, which is here the periodic Laplace operator, and then you do the potential times the density to give you the density. And everything that is not accounted for is in this so-called exchange correlation functional. You can also call it garbage collector. But the theory states there exists some functional such the solution to this problem gives you the right electronic density, but the exact function is not known. Okay, so you derive again here, you look at the first order optimality condition, you obtain this eigenvalue problem where you have now n eigenvectors or eigenfunction to solve for, and the Hamiltonian is again nonlinear through this electronic density that is built from the sum or the sum of the squares of these orbitals that is plugged in here. but you realize as well there's a nonlinear part and there's a linear part. This can be proven in this perturbation theory to be small because we have a priori results how this is converging to the exact or the exact solution of this Kohn-Sham DFT model. And the rest can be dealt with. So exactly as in the Gross-Pitaevskii, you can start off this computer plane wave orbitals and to perturb them, look for the first order perturbation, and then you can have the exact ground state energy, the plane wave approximation of the ground state energy, and the post process that is built from perturbing each of the orbitals. And the theorem states again, and under sufficient regularity assumptions on the exchange correlation functional, that you also are again 2 orders in magnitude in this convergence. However, I must say this is in the asymptotic regime, and none of the practitioners do really compute with ends or ECOTs, they call it, that is really in an asymptotic regime where you start to see things converging smoothly and steadily. However, if you look at simple, I have to say this is very simple numerical results. So it's CO2, and you have all kind of abbreviations here. But the point is that we have 8 valence orbitals here. And what I report here is this ECAT, and ECAT is somehow proportional to n square. And what it means is the maximum of kinetic energy that is given by the plane waves that live in this ball of radius n. So first, you do a constant gamma, and gamma is the relation between ECAT, and you also have an ECAT res. Since we have an n res, you have an ECAT res, and you keep this constant. Sorry, I skipped, somehow I skipped 2. Yeah, okay. So, yeah, we first, sorry for the confusion, we first fix the n or the ECAT, and then we increase this ratio, and is exactly related to Daniel's question. So we increase this annulus where we compute the residual. So if you take, for instance, here this as a starting point, you do the plane wave, you do not perturb, then the energy is always the same, but then you start to take larger and larger modes to take into account to compute the residual, and then you converge to this plateau, and for lambda equals to 3, you gain 1 order of magnitude. Since this gap is asymptotically increasing because it's an n to the minus 2 that we're gaining, if we increase here the n here, we gain now more and almost 2 orders of magnitude. And the interesting fact is that the computational time that you spend for doing this step going from here to here is about 3%. So this is the time relative to the computation without perturbation. So the point is that these DFT computations, these are nonlinear eigenvalue problems, and what this perturbation is doing is to solve the nonlinearity in this small space, so it's relatively small, and then only at the end you unfold on the full space. It's like a 2-grid method, and you project somehow or you correct in a larger space, and this is only once after many nonlinear iterations have been done. And okay, here this is the other one where you can say I keep the ratio between n and n res constant, and then I look at different factors of gamma, so how much larger the annulus should be for computing the residual, and you see different curves and different computational overheads. So let me come to my main part. Is related to this topic, but is more general. So in my opinion, mathematical aspects in computational chemistry, physics, and material science is underrepresented in applied mathematics. To illustrate this, I once typed some search phrases in Google Scholar to represent the whole community, scientific community, and in Mathsinet to represent the math community. If you take traditional fields of numerical or applied mathematics, you have good hits here, and these are very well represented in the math literature. If you go to very prominent topics in this kind of disciplines, you see a ridiculous small number of publications in the math community. And I mean, it's not that the problems are substantially different. This is about discretization of PDEs, eigenvalue problems, and so on. And if you look at supercomputer centers, I mean, you have different centers with different numbers, but they resemble each. You have chemistry and materials here. You have physics, particle physics, computational chemistry, condensed matter physics, and so on. There's always a large part devoted to those disciplines, and somehow we as mathematicians, we don't have our hands in the numerical analysis and so on. And as I said, I mean, there are several problems, and I think there are several low-hanging fruits, or we should also engage in these disciplines. But somehow it's not in our curriculum. If we teach applied mathematics, it's everything very engineer-based. And there are many abbreviations in computational chemistry. You don't have any idea if you speak about coupled cluster, Hartree-Fock, post-Hartree-Fock, LDA approximations, and so on. And in order to counterbalance this a bit, we took two measures. We first founded a GAMS activity group called Modeling, Simulation, and Analysis of Molecular Systems. So if you're interested, please send me an email and you can join. So for GAM, for the non-German audience here, is kind of the Siam of Germany. And secondly, we also prepared 5 tutorials where we give an introduction to computational chemistry from mathematicians for mathematicians, and I let you enjoy this little trailer. So this brings me to the conclusion here. So I presented a post-processing based on simple. The proofs are quite long, but the idea is nice and clean. Perturbation arguments to improve the accuracy. The additional computational overhead is very linear, especially for nonlinear problem, because you do that once at the end. The theorem I have to mention is in the asymptotic range, but the numerical results interesting for practitioners is in the pre-asymptotic regime. But we saw some simple numerical illustrations that is working. Open problem is somehow if you perturb this, the solution is no longer what's called self-consistent, and the computation of the forces for the Hellman-Feynman theorem doesn't work anymore. So there are some issues, but we're working on this. These are the references, and thank you for your attention. So which, the two-grid method or the a priori analysis of nonlinear Schrödinger equation? They did the a priori analysis. Okay, so it's the same method, but these are a priori results, yes. And that we use in order to justify, there are these terms here. Somewhere I said that the things are small and therefore we neglect it up there. Small by a priori results, and that's exactly the reference you're mentioning.
Any other question or comment? So maybe I ask one. So usually people work on this single equation, but how is it relevant to more coupled problems for Schrödingers?
What do you mean coupled?
So you have just a known one unknown here as a U. So you may have
Yes, so the DFT model, I mean, you have the original Schrödinger equation, the electronic n-body problem, is a problem in 3n dimensions, so this is unfeasible to do. Then the DFT theory tells you that it is feasible, at least in theory, to solve a three-dimensional nonlinear eigenvalue problem, which is exactly the one that is here. So here we do have many orbitals that you have to look for, right? And at the end, if you know somehow already, would know the, where is it? One more? No. If you would know the exact electronic density, then you would have a linear eigenvalue problem and you're looking for the first n eigenvalues of this operator. But these orbitals are coupled with the density through the relation that I showed at some point. So this is, yeah, it has many, yeah.